So what I'll do now is I'll just summarize not the geometric techniques, but I'll kind of summarize what is a reactive decision making, what is a reactive navigation, how do we make decisions reactively. So my mantra behind every approach is that I need to do some quick calculations, mostly arithmetic. So the complexity is minus simulation for which getting the nearest k people, getting the nearest k obstacles will be a logarithmic map lookup. So not considering the proximity queries, so given proximity queries, my complexity was, strictly speaking, a constant. I was just doing some arithmetic, some plus minus multiply divide, and therefore my algorithm can move very fast. My algorithm can move very fast. If you have a real robot, it will invoke real sensors to find out who all can it see, who all are closest, where does the laser ray strike. So with a real robot, the calculations are constant. Unfortunately, if you have a simulated robot, the proximity queries for the map will have to be given. So given positions of n agents in the world, who are the 3 nearest agents to me? And the proximity queries will be a logarithmic lookup subjected to constraints. So I wanted to do quick computations. My inputs were the nearest people, agents, obstacles, typically just 3 to 5. And we looked into position and speed as factors. And my output was immediate linear speed and angular speed. I also considered the orientation. And I do this thing in a loop. I make an immediate move, I move the agent, I again make the agent move, I again look around, I make the agent move. So my algorithm is simple, that I look around, I calculate V and omega, linear speed and angular speed, using the model, and I simply implement V and omega, which moves the robot, and this thing happens in a loop while I have not reached the goal. So it looks good, it's computationally less expensive, it's fast, it's everything that you could have desired. It's the best algorithm, it doesn't need memory. You somehow assume that you always know your location. That's the only assumption, which is practically possible now. And it appears to be the best algorithm. The only problem is, no matter what, every reactive algorithm will have as per its own modeling when it gets stuck. We looked at in detail in the potential field, where I also had randomization. Every reactive algorithm will get stuck at some or the other position, at some or the other way, and after that it's not getting out. And because it's not getting out, so there is no guarantee of optimality or completeness. So So it may not follow the best paths. You make immediate decisions. You may not get the best paths. May not get the shortest path no matter what. And you may get stuck. You may not even get a path. The agent may get stuck. That's the problem with all reactive algorithms. However, you can deal with, it's very fast. You can deal with suddenly appearing obstacles. You can deal with dynamic obstacles. You can deal with everything possible. Just keep on adding obstacles out of nowhere, just make them land. Your agent will still be able to avoid them. It's fast. The other way of working is what we looked at into the course of AI. Those are deliberative algorithms. So A-star algorithm, it's deliberative. It does all permutation and combination. If I do this, then what this happens, then this happens, then this happens, then this happens, then I do that, then maybe I do that, what really goes on. Now, the problem is that they are too computationally expensive. But they are optimal and complete. Subjected to resolution. Now the problem is, suddenly appearing obstacles, there's nothing you can do about it. An obstacle suddenly comes in front of you, the algorithm will take its own 2, 3, 5 seconds, and the robot will have to wait for the new obstacle to come. Worse is moving people. The people move, the map gets invalidated, the deliberative algorithm in 5 seconds, 3 seconds computes a new path, but then it sees the person has moved even further. So map is changing at a faster pace than what your algorithm can accommodate. And because map is changing at a faster pace than your algorithm can accommodate, you'll never be able to have a correct path. And that's what suddenly happened, and that's what practically happens, that now that the pandemic season is going on, I give you a question. Before you can cheat from here and there, I give you a new question. So it's time's up. Time for the previous question has changed. So think about writing the best answer. You don't have time. There are time constraints. Before you can have the best answer to question number 1, I've gone to question number 3. I'm not going to take solutions to question number 1. So you'll score a perfect 0. Even though your answers may be perfect, they don't come on time. And therefore, that's the interesting thing in algorithms. So when we talk about the deliberative algorithms, they do all permutation and combination. They, like the Vishwanath Anand, they do everything, and the reactive algorithms. So the time complexity is highest here and it's lowest here. When you come to, and same as memory, completeness, these are generally complete, subjected to resolution. These are not. Optimality, these are generally good at optimal. These are not. They are reactive algorithms that are actually complete, but then that's an exception. So I put generally no. And because of this, what happens is that here this is better and here that's better. What that means is, if I need to handle static obstacles, then deliberative algorithms are better. I don't care about complexity. It's static obstacle, it's not going to change. I'll take my 4-5 seconds. Optimality and completeness is dear to me. I don't care about that. Reactive algorithms are not good. They move immediately. I lose on optimality and completeness. The obstacle was static. I could have better weighted. When you talk about dynamic obstacles, then the problem with deliberative algorithms, that deliberative algorithms, by the time they make a modified correct plan, the obstacle has further moved. So you're planning at the frequency of half hertz, the map is changing at the frequency of 5 hertz. By the time you compute the answer, the question changes, the map changes. So they'll never be able to handle reactive. Very good. Suddenly appearing obstacles, So you always, so it's suddenly appearing obstacles. Let me write it up again. And thereafter it's static. So first, immediately to make the robot move, you say that, okay, let reactive algorithm carry out. So reactive algorithm suddenly makes all decisions, and you predict that after 3 seconds, this is where the robot is gonna be approximately. And then from that predicted position, you use a deliberative algorithm to replan the robot. So that's your robot. Goal, there was nothing in between. Suddenly you got an obstacle. So you make a reactive algorithm take the lead. You appear after 2 seconds. The robot will approximately be here. So from here you till 2 seconds, the reactive algorithm is going wherever. You plan a new trajectory, which is like this. Then you see that after 2 seconds, the robot was actually here. You just connect this up, and then you make the robot move like this. So that's the suddenly appearing obstacles. Now, the problem is that I've got just one algorithm to choose, whether be it deliberative or reactive. I got just one algorithm to choose, and because you've only got one algorithm to choose, you kind of say, can I have a hybridization between the two? So you say, can I hybridize? Now, this course is not on deliberative algorithms. It's a course on AI. More specifically, it's a course on robot motion planning, which is a separate course at this university, which is also where we look at hybridization in detail. So let's take a practical scenario. This is where I am taking this course, and this is my cabin, as you know, and this is a robotics classroom. So it has benches over here, and this is a robotics laboratory. There's an entrance which is right over here. And these are the cubicles at the robotics laboratory, and this is the whatever, and we've got some furnitures over here, some cubicles over here, some flower pots over here, and blah blah. So I need to go from here, which is my source, all the way up to here, which is where my student is, which is my goal. It's a static map. This is the map that the robot makes probably as soon as we get the robot into a working environment. As soon as we purchase it, that's exactly what we make. So we ask all the humans to go away, except for the robot controller. The robot goes around, it looks at all the places, and it memorizes it as a map using algorithms not a part of this course. And then we call an A-Starlike algorithm, which gives me this plan. Now I cannot travel this plan because as soon as I start traversing on this plan, there will be people who move around. So these are all the different people who are moving around, and therefore the trajectory is invalidated. As soon as I come over here, this person is coming around over here, and both me and this person will collide. So they are moving people around, and therefore what we actually do is, this is called as a deliberative path. Now, I say that currently what is the last point in the deliberative path that I can see considering only static obstacles. So it's this point. So I call this thing as the first sub goal, and I make a enlarged version of this point. So that's my map. That's my source. That's my first sub goal. And I use a potential field like reactive algorithm to decide my motion. So let's say I move around over here in this manner, and I move around over here, and somehow I have reached this point. So let this be my current position. And at this position, this is all where all the obstacles are. So now, which is the last point that I can see, considering only the static obstacles. So there's a door over here, and that's blocking my view. So this is the last point which is visible. So this is what I say is my current sub goal. The last point visible in the trajectory. And now let me plot this thing up separately. So that's what the map is going to be. So that is this line. This is where I am currently. So that's my source. This is my sub goal. So that's the door that I was concerned about. And there are obstacles like this. So these are dynamic obstacles. Now what I'll say is I don't care about the static obstacles. As you can see, they're far off. I only care about these dynamic obstacle. So now I will apply, let's say, a velocity obstacle method in pursuit of this sub goal. So I'll say, okay, this is about to cross. This is also about to cross. So I should probably go in between these two. So I should go here. I'll not care about the static obstacle, velocity obstacle method. I'll not care about this because it's going somewhere else. So I'll be over here, and my sub goal will be here till the point I can see it. If I can see a distant sub goal in this path, then I will go with that. And soon by velocity obstacle, I'll actually end up avoiding these two people pretty safely. That's what the velocity obstacle does. Without wrapping myself up, I'll avoid them up. And once I avoid them up, so this goes here, this goes here. Once I avoid them up, this goes here, then is when I'll start seeking for my sub goal. And as soon as I come here, what will happen is I'll be able to see a much more distant sub goal. So the mantra behind these things are, number one, whenever you cannot reach a goal by a reactive technique because it's not trap free, reach a sub goal. A sub goal is nothing but something which is easy to reach. It's easy to reach because if there were no dynamic obstacles, I would have just walked in straight to the sub goal. Here I am. So if you cannot reach a goal, reach a sub goal. And in order to reach a sub goal, it's a very simple situation. All dynamic obstacles, and that's why when I said that they are only dynamic obstacles, I did not have an iota of concern. So consider only dynamic obstacles, avoid them up, and once you avoided them up, go to your sub goal. Once you're about to reach the sub goal will move further away. It'll keep on moving till it reaches the goal. So whenever we actually have robots, that's exactly what they do. They cannot use a deliberative algorithm because people are moving. They cannot use a reactive algorithm because mostly it is trap prone. So if I start using a reactive algorithm for this situation, it'll try to break this wall, potential field, and it'll get trapped. So I can neither use a deliberative algorithm practically nor a reactive algorithm. All that I do is I get this picture as soon as I buy a robot. Every agent knows its map. You know your home. And we make this map using custom libraries. We plan for this deliberative path, AI calls. How do we do that? And we just plant sub goals on this path. And reactive algorithm, it only avoids the dynamic people. And because it only avoids dynamic people, once it's able to avoid the dynamic people, it tries to reach the sub goal. Till that point of time, somebody keeps on moving the sub goal further away. So because somebody keeps on moving the sub goal further away, the robot keeps on trying to reach the sub goal, avoiding all the other people on the way. And it's about to reach the sub goal has further moved. Then it also avoids other people trying to reach the sub goal further moves away. And that's how every navigation happens. And therefore, that's exactly what you see, that when I fuse them up, the static obstacles were handled by the deliberative trajectory, which was this blue trajectory over here. It handles all the static obstacles. The dynamic obstacles were handled by the reactive technique. So that's what happened. So avoiding both these people and taking this path, the velocity obstacle method or the reactive technique was responsible for it. And the fusion is that the static obstacle avoidance technique gets the actual goal, and the dynamic technique, which is reactive, will only get the sub goals. It does not have the vision to reach the main goal, so it only keeps getting the sub goals as an input and tries to get the sub goal. And using the fusion of the two, we are actually able to avoid both static and dynamic objects. So here most of the reactive components are what we are studying right now. All the deliberative algorithms and all the issues over it is a completely separate course that I take. And therefore, I said that without considering the static obstacles, only considering the dynamic obstacles, we'll just look at the future, we'll just look at the behaviors of the agents without caring about where does it go in the bigger picture, because that's a separate course on planning. So, overall, summing it up, we saw in the reactive planning navigation how just by looking around different people and the way they behave, I can invoke different kinds of behaviors, currently only obstacle avoidance and goal seeking. In social potential field, of course, you could get attracted towards different people with different degree, resulting in interesting behaviors. And we saw how do I essentially control my agents using a linear and an angular velocity, so that they display the desired behaviors and get to their desired goals. And the mantra is that these are extremely simple calculations that the robots can do on the fly, the agents can do on the fly, and display all the complex dynamics at the macroscopic level that you see everybody displaying all around. And with this, we finally conclude the day. Thank you for a patient listening.